Hey everyone, and welcome back. Today, we're going to lift the hood on the invisible magic that makes our digital world feel, well, fast. We are talking about caching, the absolute secret weapon behind every single high-performance app and website you use every day.
You ever wonder about this? You tap on one app, and boom, everything just loads. You open another one, and you're stuck staring at that dreaded loading spinner. More often than not, the difference between those two experiences comes down to one thing: how cleverly they use caching. And the difference is just staggering. Seriously, the right caching technique can make data access up to 50 times faster. That's not just a little boost, that is a complete game changer. Caching is the hero of our story today, the thing that turns sluggish, annoying systems into these lightning-fast experiences we all love.
So here's what we're going to cover. First, we'll talk about why we even need this stuff, the need for speed. Then we'll see that caching is everywhere. After that, we'll get into the caching playbook, the actual strategies. Then, how do we keep things up to date? That's keeping the cache fresh. And finally, we'll look at what happens when caches go wrong.
Okay, let's dive right in. For pretty much any application that has to handle a ton of read traffic, think about your social media feeds, e-commerce sites, news websites, you name it, the database is almost always the biggest bottleneck. It is the one slow point that holds everything else back.
And this slide right here shows you exactly why. A database usually has to pull data from storage, like a spinning hard drive or even a fast SSD. That takes time, maybe around 50 milliseconds. A cache, on the other hand, is an in-memory store. It's using something like Redis, and it serves data directly from RAM, which is just orders of magnitude faster because it's physically so close to the CPU. The result? You get a response in about 1 millisecond. That is the 50x speedup we were just talking about.
All right, let's move on, because when we talk about caching, it's not just one thing sitting in one place. Not at all. Modern systems use what you can think of as a multi-layered defense against slowness, and each layer of the cache has a very specific job to do.
So just think about the journey a request takes. First, step 1. Your phone or browser checks its own local cache. If what you want is there, great, it's instant. If not, the request moves on to step 2, a content delivery network, or CDN. This is how Instagram can serve you a picture from a server that's in your city, instead of pulling it from halfway across the world. Still no luck? The request goes to step 3, a tiny, super-fast cache that lives inside the application server's own memory. And only if all of those layers miss does it finally hit step 4, the main external cache, like a big Redis cluster. That's the last line of defense before we have to bother the slow database.
Now this is where it gets really interesting. How do applications decide when and how to put data into the cache in the first place? Well, it turns out there's a pretty well-defined playbook for this, with a few core patterns that cover almost every situation you can think of.
Okay, the first and most important pattern you have to know is called cache aside. You'll also hear it called lazy loading, and this is the default strategy for a reason. It's brilliant in its simplicity. Instead of trying to preload everything into the cache, the system only caches data the very first time it's actually asked for. It's lazy and very efficient.
The logic is really straightforward. Your app asks the cache, "Hey, do you have the data for user 123?" If the answer is yes, that's a cache hit. It gets sent back instantly. Awesome. If the answer is no, a cache miss, no problem. The app just goes to the database, grabs the data, saves a copy in the cache for the next time someone asks, and then sends it back. For most read-heavy apps, this is the perfect balance. Now, there are other more advanced patterns too. A write-through cache, for example, updates the cache and the database at the same time. This is perfect for something like Ticketmaster, right? You absolutely cannot show someone that a ticket is available when it's already been sold. The trade-off? Writing data is a bit slower. Then you have write behind, which is the opposite. It makes writes feel super fast because it updates the database later. The risk? If the cache crashes before it saves to the database, you could lose that data. See? It's always about trade-offs.
Okay, so we're constantly adding new data to our cache to make things faster. But here's the thing, caches don't have infinite memory. So that brings up a really important question. How do we keep the cache from getting totally clogged up with old, useless, or stale data? This is where eviction policies come into play, and you can think of them like the bouncers at a very exclusive club. When the cache is full and a new piece of data wants to get in, the eviction policy is the one that decides who gets kicked out to make room.
The most common policy by far is LRU, or least recently used. It works on a simple assumption. If you haven't used a piece of data in a while, you probably won't need it again anytime soon. So out it goes. It's a fantastic default. Then you have something called TTL, or time to live. Now, this isn't technically for eviction, but it's crucial for freshness. You just set a timer on each item, say 60 seconds for a news feed, and after that time is up, it just disappears, forcing the app to get a fresh copy from the database.
So at this point, caching probably seems like a silver bullet, right? Just add a cache and poof, everything gets faster. But in the real world, it introduces its own set of unique and sometimes really tough problems that engineers have to deal with. So the first major problem we need to talk about sounds pretty dramatic because it is. It's called a cache stampede. You might also hear it called the thundering herd problem.
Just imagine this. The link to the final score of the Super Bowl is cached for 1 minute. The whole world is watching. At the exact millisecond that minute is up, what happens? Thousands, maybe millions of people all requested at the exact same time. Every single one of them gets a cache miss, and they all stampede straight to your database, all at once. That can easily crash the whole system.
Now, to prevent this, engineers use some really clever tricks. One is called request coalescing. The basic idea is that only the very first request is allowed to go to the database. Everyone else who asks in the next few milliseconds is told to just wait, because that first request is busy repopulating the cache for all of them. Another approach is to proactively warm the cache by just refreshing super popular items right before they're scheduled to expire.
All right, the next big challenge is what happens when a single piece of data becomes too popular. This is what's known as a hotkey problem.
Think about Taylor Swift's profile on X during a new album drop. The cache key for her profile might get millions of requests a second. And even though that data is in a cache, all that traffic is hammering a single server in the cache cluster, which creates a whole new bottleneck.
So the solution here is pretty logical. You have to spread the load. You can replicate that hotkey, make copies of it across multiple cache servers, and then balance the traffic between them. For really extreme cases, you might even add another tiny, even faster cache layer inside the application server itself, just to handle that one viral item and protect the main cache from the flood.
And this quote right here just gets to the absolute heart of the matter. Yes, caches make things faster and take the pressure off your database, but they force you to deal with new problems, like making sure your data doesn't get old and stale. It's a trade-off.
So the crucial point to take away from all this is that caching is not a magic fix. It's an engineering trade-off, plain and simple. You gain incredible speed and the ability to scale, but you take on the responsibility of managing data consistency, new failure modes, and all these complex edge cases. At the end of the day, there is no free lunch in system design.
So, the next time you open up your favorite app and it feels just ridiculously fast, take a second and think about it. You're probably not just seeing a well-built app, you're experiencing a masterfully designed, multi-layered caching system with all its pieces working in perfect harmony. Hope you enjoyed this one.